Hi. So in this experiment, we're covering one new analytical technique that's very useful in chemistry called spectroscopy, and also introducing a another calibration method, the external calibration method. So spectroscopy. This is relying on the interaction between light and matter. Light and matter. So you may remember from a very basic general chemistry um, understanding, we might have something that has two energy levels and an electron in one level. And if you bring in a photon of the appropriate energy, it can excite that electron up to a higher energy state. Okay? And similarly, if you have an electron in a higher energy state, it can relax back down into the lower state and emit a photon. Okay? So spectroscopy is a method where we take advantage of this phenomenon, and it allows us to measure this, either the absorption part or the emission part. Oops. So there are a lot of different analytical techniques that use this phenomenon of um, absorption or emission. So in this experiment, we're going to be doing atomic absorption, and that's really useful for atoms. If you have molecules, you might be more interested in looking at UV visible spectroscopy because molecules tend to absorb in that range. You can look at electronic transitions, or you could look at vibrational transitions, doing things like infrared spectroscopy. There are a bunch of different applications for this, but the main thing to take away is that it relies on the fact that every species will have unique energy levels. And that helps allow us to either identify components of a mixture, or we can look at concentrations of a certain species because we can identify it and things like that. So in this experiment, like I said, we're doing atomic absorption. And it may seem obvious, but I just want to clarify that this means that we can analyze atoms. Okay, so molecules we cannot analyze with atomic absorption spec, only atoms. And we're looking at absorption. Specifically, we're looking at electronic transitions. Okay, so every atom, kind of like in our simplified drawing, has its own individual wavelength that it can absorb for its different energy level transitions. So we're only looking at absorption, this first situation. We are doing no emission analysis here with this instrument. Okay, the instrument we're using is a flame atomic absorption spec, AAS. Okay, and some applications for this instrument, like I say, it's really good at identifying atoms, and we're going to talk about Beer's law in a second. So this method is commonly used for identifying heavy metals in environmental samples, for example, in water analysis, to make sure that our drinking water is good and safe. And in this experiment, we're looking at the calcium concentrations. So we're trying to determine the concentration of calcium in seawater. One reason that's important, calcium carbonate is what a lot of shelled ocean life uses. Calcium carbonate is their shell, so the concentrations of calcium in seawater is important for those creatures. So let's go over a little bit. What does a flame AA look like? I'm going to take up the next page to do this. So one thing, we have our seawater solution. Maybe you're thinking, well, calcium in a solution is going to exist as an ion, right? Calcium 2+. How are we going to get it into atomic form, since that's what we need to analyze? So if we start off with our sample in its liquid form, we need to go through a series of steps in order to atomize. The first one of those is to send it through a nebulizer, and that takes our sample and turns it into aerosol particles, so little droplets suspended in gas. Okay, aerosol. And next, the next segment, the next few steps, essentially our aerosol have entered the flame of our AA, and so this all happens because we're at high temperature. But the next step is what's called desolvation. The heat helps to evaporate off all the solvent of those aerosols, and you're left with just ionic species for a brief moment. Okay, ionic species. But soon after that, in the intense heat of the flame, we get atomization, where those ionic species are broken up and you're just left with neutral atoms. Okay. My artistic talent of drawing a flame. Okay, so all of this is happening inside the flame. And in the AA instrument that we use in this lab, we're using an acetylene air mixture to fuel that flame, and that creates a flame of roughly 2300 degrees Celsius. Okay. Now we have our sample atomized in that flame, and what we're going to do is send light through our sample, and the sample, those atoms, if hit with light of the appropriate energy, will absorb the light. Okay, so, and we'll be able to detect, okay, our lamp had an initial intensity. It went through the sample and some of it got absorbed, so the intensity that comes out the other side is going to be lower, and we can detect that intensity change, essentially. So let's start off my simplified drawing of a lamp. We'll have a lamp on this side, but need to make it clear, it is not a tungsten lamp like my little drawing kind of indicates. It's actually a special lamp called a hollow cathode lamp. Okay, in atomic absorption spectroscopy, we are looking at specific atoms. So in this one, we're looking at calcium, and we know the wavelengths that calcium would absorb. So we make these specific lamps that only emit those wavelengths. Okay, it's a wavelength specific lamp. And the way it works is there's an electrode that's coated in calcium. Or whatever material you are trying to analyze. So if you're trying to look at lead, the electrode would be coated in lead. And that means it can only emit the the same wavelengths that would be absorbed because it's the same atom on the lamp and same atom in your sample. Only wavelengths that analyte will absorb. So this is super useful. It makes our AA instrument very selective. Even though our seawater sample has a bunch of stuff in it, we can specifically just look at the calcium in there because our lamp emits a wavelength that only the calcium is going to absorb. Okay, so this lamp, like I say, it has an initial intensity I naught. And if we were to just run blank DI water through our flame, the intensity that would come out, I, would be equal to I naught. We'd have 100% transmittance. That ratio between I and I naught would be 1. And yeah, but as we start sending sample through, we're gonna start seeing the sample absorb some of that light, and this I will be smaller than I naught. And so we have this Beer's law relationship. Okay, as the concentration of our sample increases, we're going to have a lower transmittance of light, or in other words, a higher absorbance. Okay, the last few components of our sample, which I didn't give myself a whole lot of room to write. One is a monochromator. Here, let me. All right. First thing up is a monochromator. Okay, a monochromator is essentially a wavelength selector using a series of mirrors, lenses, gratings. Okay, the reason we might want to use a wavelength selector in this situation is that our flame emits a bunch of random wavelengths, and we want to make sure, since we only care about that one wavelength that our hollow cathode lamp is emitting, that's the only thing that we're picking up on our detector. So this is going to help reduce any noise. Reduce noise. Okay, and lastly, this all leads to a detector, which commonly for spectroscopy is what's called a photomultiplier tube, or PMT. Okay, so that's the general setup for a flame atomic absorption instrument. Now, some things to think about. I mentioned this Beer's law. So as concentration increases, we decrease the transmittance because there are more, sample species to absorb that light. So in other words, our absorbance increases. But there's something to keep in mind. What if our concentration is too high? We need to start thinking about our linear dynamic range of our instrument. So at high concentrations, unfortunately, then we start having interactions between our analyte particles themselves, and that can affect the absorbance. Okay, so that means we might have something like this. Our instrument response, if we, where this is concentration and this is absorbance, if we send samples of low concentration through, we might get a linear response, but as we get to high concentrations, it might start dying out, okay? Which means that we can only really make a calibration curve on this linear range. And for calcium, this linear range stops at around 50 ppm. Okay, so we want to keep that in mind. Because we need to be within that range, that means we're going to need to make some dilutions. In order to make sure whatever sample we send through our instrument is within the linear range of the instrument. So that's going to lead me to some procedural notes for this experiment. First of all, we're adding lanthanum to every sample. Okay, the reason we add lanthanum is, let me scroll back here for a second. We're putting our sample through this flame in the atomized form, but this is so hot that it could actually go back and re-ionize our atoms, and we don't want that to happen. We want all of our solution to be in atomic form because that's what absorbs that specific wavelength. So we add this lanthanum, which is an ionization inhibitor. It's going to help keep our solution in atomized form. Okay, we're going to make a DI blank, just plain DI water, and that's going to be used to zero the instrument. But we're also going to make what's called a reagent blank. The reagent blank is going to be DI water plus the lanthanum, but nothing else. Okay, so that's going to help account for how the lanthanum might affect our instrument response. Maybe the presence of lanthanum causes our detector to detect something, and we need to make sure to account for that. Okay, account for how the lanthanum affects instrument response. Okay, you'll also be making a series of standards, and you will have your unknown seawater. Okay, so relating back to this idea of the linear dynamic range, we need to make sure that all the standards we make are within that range, and our seawater is also within that range. So that means our standard should be somewhere between 0 and 50 ppm. And our unknown seawater, just note that it's approximately 400 ppm. Okay, assume seawater is roughly 400 ppm of calcium in it. So you'll need to dilute that down so that it's within the same range of the standards. Okay, I've been talking about linear dynamic range, making standards, and all this stuff, but what is this method really called? I'm referring to a calibration method called external standards. External standards calibration. You are probably familiar with this. You have probably done this in a general chemistry lab, but the idea is that you make a series of dilutions of a standard solution. in this case, it'll be of calcium 2+. So if you start with some possibly a solid form of calcium and you make a solution, and then you can dilute it to, like we said before, within 0 and 50 ppm, and make a calibration curve with those. And just remember that dilution equation might look something like this, where you take the concentration of your initial solution, multiply it by the mass of that solution you would need in order to make a solution with a final concentration of C2 of some final mass. You may have seen this formula before as M1V1 equals M2V2, but I think it will be helpful for you to write it in this format, because again, in analytical chemistry, we no longer use volumes. And the M is usually because we represent concentrations in molarity in Gen Chem, but now concentrations, as we have learned, can be different units other than molarity. Okay. Okay, so we're going to make a calibration curve. Oops. And this calibration curve will show us how the instrument responds to different concentrations of the analyte. Okay, one thing I would like to point out, however, the external standards calibration method does have one downside to it, and that's the fact that you make these dilutions of the standard in deionized water, but then our sample has a much more complex matrix because it's seawater. So that might be something to think about. How reliable is it to compare our complex matrix measurement of absorbance to this calibration curve that's made in DI? Okay. Okay, but our calibration curve might look something like this: concentration versus absorbance. You make a series of standard dilutions with known concentrations, and you can make a trend line through there, which has y equals mx plus b, and then you can find the concentrations of your unknowns by just plugging in those measured absorbances in for y and solving for x, right, to get their concentration. Okay, that's just about it. The last note I want to make is, as per usual, you want to discuss your accuracy and precision. On the topic of accuracy, the literature value for how much calcium is in seawater comes down to this idea that 1.2% of salinity is due to calcium. Okay, and if we say roughly salinity is equal to 35 parts per trillion, you should have, however, in your density and salinity experiment in that lab report, you determine the salinity of this seawater that we've been using. So it would be good to use your value for salinity. And cite yourself. Okay, when you cite that literature value, you can go ahead and just cite your own lab report. That is acceptable. Okay, so if 1.2% of the total salt content is due to calcium, that means 0.012 times 35 parts per trillion. That's 0.42 parts per trillion. And again, just breaking down units, parts per trillion is the same as grams per kilogram. So for every kilogram of salt water, we have 0.42 grams of calcium in there. Similarly, we could convert that to ppm, which is the same as saying we have 420 milligrams in a kilogram of seawater solution. Okay, so you should do this yourself, but plug in your own salinity value right here and get an answer in ppm, and then compare that to these concentrations that you get from solving your calibration trend line for the concentration of your seawater samples. Okay? Cool. Have fun.